Hi, I am Lopamudrashen. Welcome back to my channel Electronic Science Tutorial. I will start a new lecture series on NTA UGC NET and West Bengal SET exam for Electronic Science subject. Those who are not follow my channel, please follow my channel. If you like my channel, then please like, share and subscribe my channel. So let's start our class. In today's class, we discuss about the NTA UGC NET and West Bengal SET exam 2022. In this session, we cover in detail about this topic so that we can easily solve the previous year question paper of UGC NET Electronic Science. Each and every topic we can understand in easy and simple manner. So, let's begin our NTA UGC NET exam 2022 class. Okay. Today I will talk about the PN junction diode under forward bias condition. In previous class we talked about the PN junction under zero applied bias or under no bias condition. Today I will talk about the PN junction under forward bias condition. Forward bias mean what does it mean? It means when P side of the diode is connected with the positive potential of the power supply and N side of the diode is connected with the negative potential of the power supply, this connection is called forward bias condition or forward bias connection. So this is the structure of PN junction under forward bias condition. This side is P side and this side is N side. In P side, we know the majority carrier is holes and the minority carriers are electrons, and in the N side, majority carriers are electrons and the holes are the minority carriers. And the P side of this diode is connected with the positive potential of the power supply, and N side of this diode is connected with the negative potential of the power supply. So this is the forward bias condition. So this is the external voltage we applied here. Okay. So this forward bias condition is also called on condition. On condition, why it is called on condition? Because the current will start flow through the device. So this is the on condition. We can say this condition is, or the forward bias condition is called the on condition. So this on condition is established by applying the positive potential to the p-type material and the negative potential to the n-type material, right? So the application of a forward bias, that means V, okay, will pressure the electrons in the n-type material and holes in the p-type material, which are the majority carriers in the two sides, and this pressure recombine with the ions near the boundary region and reduce the width of the depletion region. So the majority carrier of the holes and the majority carrier of the electrons in the p side and n side respectively in the boundary region recombine with the ions and reduce the width of the depletion region. So what are the minority carrier are doing? Minority carriers, the resulting minority carrier, that means electrons from the p-type material to the n-type material and holes from the n-type material to the p-type material, has not changed in magnitude because the conduction level is controlled primarily by the limited number of impurities in the material. So this has not changed in magnitude. So the minority carriers of electrons from p side to n side and holes in the n side from n side to p side has not changed in magnitude, right? Okay, but the reduction in the width of the depletion region, is reduced, so it resulted a heavy majority flow across the junction. An electron of the n-type material now reduced barrier at the junction due to the reduced depletion region, and a strong attraction for the positive potential applied to the p-type material. As the applied voltage or the applied bias increases in magnitude, that means if we increase the bias voltage, okay, the depletion region will continue to decrease in width. The depletion region width is continue to decrease until a flood of electron can pass through the junction, and which result in an exponential rise in current, okay, under forward bias condition. So this is the structure of or the basic concept of p-n junction under forward bias condition. Now, what is the energy band diagram of p-n junction under forward bias condition? So this is the energy band diagram of the forward bias p-n junction. We know that in thermal equilibrium condition, in previous class we already discussed about this topic, that is the Fermi energy is constant throughout the system when we consider the thermal equilibrium condition. But when we apply forward bias, that means forward bias changes the thermal equilibrium and it also changes the Fermi energy level. And this is the band diagram of a p-n junction when negative voltage is applied to the n region with respect to the p region. Okay, so this is a p-n junction with an applied forward bias. The net electric field is due to the reason that applied electric field oppose the built-in depletion region potential barrier. As the energy bends at the forward bias condition shift due to the applied bias, and the Fermi level on n side, that is EFN, is above EFP by the energy due to the applied voltage. Okay, so EFN is lies higher energy than EFP in the p side, and this is due to the applied voltage, and this is the applied voltage EVA. VA is the applied forward bias voltage, and for this voltage the Fermi energy or the thermal equilibrium condition of the Fermi energy level is break throughout the system. And what we saw here, that is we saw here that the Fermi energy in the n side is higher energy than the Fermi energy level of the p side. So the barrier potential is reduced by the applied voltage, and that is equal to EVBI minus VA. So this is the basic concept of energy band diagram of the forward bias p-n junction. Okay. So here we end today's session. I hope you understand this topic. Thank you. With this, we have come to the end of our session. I hope you like this video. Thank you, friends. If you like my video then please do like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.